Cheers. Can people hear me? Good. Can everyone see the slides?
No.
I'm going to go slide. Can you see them now?
No.
Well, okay, fine. Sorry, the slides are. If you can't read the slides, they are on my website. So if you're at the back, if that's easy to read, then you can do that. So, hello. Thank you all for coming to this session. Today we're going to talk a bit about testing. Testing is a really important part of software development. It helps us catch regressions, spot bugs, make sure that our code is generally behaving correctly. And without tests, we literally would not be able to do our jobs. And what I'm going to talk about today is something called property-based testing. Property-based testing is a very powerful approach to testing that lets you write very robust code without having to spend an arm and a leg. So we're going to talk about three things in this session. We're going to start by talking about what is property-based testing? What's it all about? Why should you be interested? Then we're going to talk about a Python library called Hypothesis, which allows you to do this sort of testing. And finally, we're going to look at some examples of how you can actually do this sort of testing in practice. So let's start by asking, what is property-based testing? And to answer this question, I think it's instructive to start by thinking about the way we normally do testing, which is often called examples-based testing. In examples-based testing, let's suppose we've got some bit of code, some function we want to test. The way we would test it is we'd start by writing down some example inputs to the function. You know, what sort of things do we expect our code to be called with? Because we know exactly what the input should be, we can write down exactly what the output should be. And then we can just tell the computer, well, go and run the code with these specific inputs and check that the output is exactly what we expect. And the computer does this and it tells us the test passed, the code is working. So a typical example of this, let's say we're sorting a list of strings. I'd write down some lists of strings, I'd write down what they sort to, and then I can code this in a test telling me that we'll go through, sort the list of strings and check that it comes out correctly. Are people generally familiar with this kind of testing? This is a fairly common pattern. This is also not a very good test. I should say, if this is the only test we write, this is much better than not having a test, but really all this test tells us is that these four examples of strings lists sort correctly. It doesn't tell us about the general case. It doesn't tell us how good this is as a sort function. Because we don't have good coverage of the test cases. We're only testing a very particular hand-picked set of cases. So we could write more examples. We could continue writing examples right off the bottom of the slide, into the floor, and down into the basement. But there are a couple of problems with this. One is, that's really boring. Somebody's got to sit down, think of the examples, write them into your test suite, make sure they're correct. Nobody wants to do that. And that's how we end up with test suites with patchy coverage. It's also hard to maintain. You end up creating a test suite which has a lot of hand-coded examples, it's very brittle, and somebody's got to make sure those examples are correct. Test code is not magically immune from having bugs just because it has the words test in it, and it's easy to write test cases that are actually broken. But the biggest problem is that it's easy to miss edge cases. Okay? If there's a sort of example you didn't think of when you were writing your test cases, your code is not going to tell you anything about how, your test will not tell you anything about how your code copes with that. And if you're anything like me, you write tests at the same time as you write the code because you're a good developer. But then if you forgot to write cover an edge case in the code, will you forget to remember to test for it afterwards? It's unlikely. The problem is that coming up with random, unbiased examples to use in your tests is really quite hard, and humans are not very good at it. But it turns out we have these magical machines called computers. Computers are very good at doing boring, repetitive tasks that humans don't want to do. So why don't we let the computer come up with our examples? That's the basic idea behind property-based testing. So in property-based testing, rather than specifying the exact inputs to our test, we just describe them. We tell the computer what sort of input we would like it to use. Now then, of course, because we don't know what the exact inputs are, we can't say what the exact output should be, so we have to give the computer some other way of determining if the test has passed. So we have to describe the results, and these are the properties. And finally, we let the computer pick examples. And because computers are really, really fast, it can draw lots of examples very quickly and throw them into our code and see, can it cause the test to fail? So let's think about what that might look like for our example. Hopefully, if we're sorting a list of strings, hopefully the input is in the name, it's a list of strings. But how can we tell the computer if the test has passed? We can't compare it to the exact result. So how do we know if a list is sorted? Well, a sorted list is a list. It's not a tuple, it's It's not a string, it's not a float. If we get any of those, we know it's done something wrong. A sorted list has the same items as the original list. If we've gained items or thrown them away, we know that the sort function has done something wrong. And of course the sorted list is ordered. It turns out if we can test for these three conditions, we actually have a much stronger test than the test we started with, because this is testing the definition of a sort function. It's not testing a few hard-coded examples. And it turns out we can test this, and that's what that code looks like. And this is a really neat, compact test. You pass in a list of strings as an argument. The computer will then check it against the three conditions, and if it exits cleanly, we know that the list has been sorted correctly. The difficult part then is coming up with the randomness of strings, but we're going to leave that bit to the computer. What this style of testing gets us is a much more powerful test, because by trying hundreds of examples, there are two things that can happen. Either the computer finds a bug, and that's probably a bug we didn't know about before, so yay, or all the examples pass. But now we've got a much higher degree of confidence that our code is working correctly than the 4 hard-coded examples we started with. We can be much more certain that the code is probably behaving correctly, because it's being explored with many more examples. So how do we come up with these random examples? We could break out the random module and do it ourselves, and in the spirit of over-engineering, that would be a thing that a lot of us would try and do. But instead I want to suggest that you should look at a Python library called Hypothesis. So Hypothesis is probably best known as a property-based testing library for Python. That's what most people use it for. Really what it's good for, though, is generating random data, or not quite random data, actually structured random data, and we'll see what that means in a minute, which is obviously exactly what we want for this style of testing. It's inspired by a Haskell library called QuickCheck. QuickCheck was the original property-based testing library. That's where these ideas come from. They come from the world of functional programming, but there's no reason they can't be used in other languages like Python. Integrates with all the standard test runners, PyTest, nodes, unit test, all that stuff. You don't have to run special tests on the side just to do Hypothesis. It goes right in your main test suite. And it's written by David McKeever. David is with us at the conference today, so if you have any hard questions I can't answer, David will answer them instead. David's in the purple t-shirt. So, how do we use Hypothesis to take that test stub and actually supply some random examples? Well, this is it. It's not that different, and all I've added is this decorator at given st.lists, st.texts. And this given decorator is the entry point to a test with Hypothesis. It's going to draw random examples according to the strategy we pass it. Strategy is sort of a recipe for random data. And it's going to pass them very quickly to our test function and see if it can raise an exception. And it will do this up to 200 times in a fraction of a second. And that gives us 200 examples that we can test our code against. 200 examples that tell us, hopefully, our code is passing correctly. Or it's going to find a failing example and tell us, no, the code is broken, go and fix it. So this is a very compact test. This is only, 6 lines of code plus 2 imports. That's less lines of code than the original forecast test suite, but this is a much more powerful test. That's what Hypothesis gets us. But the nice thing is that even though it's trying these hundreds of random examples, it's only going to show up as one test in your test run. You're not about to be swamped with passing test results. So I want to show you a few features. Hypothesis is a very big library, got lots of nice features. I want to show you a few features of Hypothesis that make it a really powerful library for this sort of testing and make it preferable to the alternative, which is just generate your own data with the random module. So the first one are these things that Hypothesis calls strategies. Strategy is just a recipe for random data. It's telling the computer what sort of data you would like to generate for your test. Hypothesis has strategies for all the built-in types, numeric, strings, collections, all that nice stuff, so you know all the basic types. But it's also really easy to put strategies together or write your own. So a lot of your code I imagine deals with custom classes, custom structures. Hypothesis can deal with, it's really easy to build those using Hypothesis, generate test data that precisely fits your tests. Let's look at a few examples. And it's just much easier than Java random data. It is just a couple of lines of code. You can build really complex strategies. Trying to do this by hand gets really messy really quickly, and you don't get some of the nice stuff we'll see in a minute. So this, for example, is the sort of random Unicode text that Hypothesis generates, if you call it, text strategy. These are really horrible Unicode strings that will find edge cases and bugs in your application that you do not think to test. Because most people, when told to test with Unicode strings, try ASCII. That's it. Some of these characters do not even render in my browser. That's how weird the example generates are. Also really easy to go and test competence strategies. So here we're creating a list of integers. And again, these integers tend to be bigger, messier, nastier than the sort you would do if you're hand coding your examples. So, it's going to go and search out those corners of your application that break. And here I'm even creating a custom person class. I can use the build strategy to create custom instances of that class. And you'll see I'm also filtering the strategies, so I can really easily shape the data that Hypothesis is giving me. I can tell only draw names that are from the ASCII character set. I know there are names that don't have ASCII letters in them. That's the example I'm using. You could generate, age between 0 and 100, stuff like that. It's a really rich and easy API for generating random data that precisely fits our tests, and then it's going to do the hard job of actually thinking of the examples for us. That's the first thing you get with Hypothesis. Now let's think about what happens when Hypothesis finds a failing example. The examples you saw on the previous slides, they were pretty messy, pretty complicated. And that's not really what you want to get when it finds a problem. Smaller examples are easier to debug, they're easy to assess, they're easy to work out why on earth is this test failing. And Hypothesis, luckily, one of the things Hypothesis knows is how to shrink a strategy. So once it's got an example, how does it make that example simpler? And it's probably a lot of techniques that you're probably all familiar with, delta debugging, binary search, binary dissection, that sort of thing. But again, the computer is really, really fast, and it can try these techniques way faster than we can. So why not get it to try doing all of these dissections, all of these shrinks for us, before it presents us with the failing example? And that's precisely what Hypothesis does. So here is a dubious proposition about list sorting. I assert that if we combine two lists and then sort them, that's the same as sorting the two lists individually and putting them together. We would not expect this test to pass. It doesn't. But let's look at the example Hypothesis gives us as a fact. This is the output from a Hypothesis test. I'm just using PyTest. We get the traceback telling us exactly where the test failed, and then it gives us this falsifying example. Prints a single example that is runnable code. We could just go and put that in our console, run it, and that will precisely reproduce the failure for us. Very easy to reproduce Hypothesis failures. But then the example it's given us, it tells us, I tried the list with element 1, and I tried the list with element 0. That's a really simple example and makes it really easy to see where this test falls over. But Hypothesis didn't get lucky. It didn't try that list by magic and discover that failure. In fact, if we look at some of the examples that Hypothesis tried, some of them were really messy. This is a sample of what it tried all the way down. First list it tries really messy, you see, then it tries shrinking the size of those lists, then shrinking the elements in the lists. In the penultimate example, it actually shrinks a bit too far, finds an example that doesn't fail, but finally it lands on the really small example. And it knows how to shrink its strategy and give us these really nice, simple examples that are much nicer for us to debug. And that's something else you wouldn't get if you just roll this yourself by hand. So finally, let's think about flakiness. Okay, Hypothesis, although it tries many more examples than you would try, it still only tries a finite number of examples. And some failures are really rare. So Hypothesis tries by default 200 examples a time. You can increase that, but there are always going to be bugs that occur less than 1 in 200 times. If we were drawing truly random examples, we might not hit it every time. Sometimes we draw a really bad example, sometimes we wouldn't, our tests would be flaky, and flaky tests are actually worse than not having any tests at all. Because what they do is add noise to your test runner, and they mask the possibility of legitimate failures. So wouldn't it be great if once Hypothesis finds an example, it would keep failing that example, and so our test wouldn't become flaky. And it turns out that Hypothesis does just that. It has an examples database, and when it finds a failing test case, it puts that example in the database, and then the next time it runs that test, it looks in the database and says, hey, do I know any interesting examples? Let me try those first. And that means that once Hypothesis has found a failure, it's going to keep failing on that test case. It's going to keep dragging up that example and causing your tests to fail until you either fix the bug or tell Hypothesis that that was a bad example. And this turns this from something that is just an interesting science experiment into something you could run in a production continuous integration suite. So let's look at an example. I'm embarrassed to say this is based on code I actually wrote and shipped. And some of you will already spotted the mistake. It's this line here. I'm computing somebody's next birthday, which means adding a year to the current date. And if you try this on the 29th of February, the data time library will be unhappy. This sat in our code base until late February this year. But I've written a simple test using a hypothesis that asserts somebody's next birthday falls after today, which is hopefully not an unreasonable assertion based on the definition of the word next. I then ran this test 50 times. I ran this test twice, 50 times. First round, I deleted the database every time, blew away its cache, so hypothesis drawing truly random data each time. The second time, I let it keep the examples database running. And this is what those tests look like. In the tests without any caching, where it's drawing random examples, the test fails flakily. We get 6 failures on 50 runs. So that's below the level of noise that you might say, oh, there's probably a bug in the test suite, we'll fix it next week. And then the week after that, and the week after that. And all at that time, this is masking potentially legitimate failures for our application. Meanwhile, in the case with caching, it takes a little while to spot the failure. 29th of February is about 1 in 1,000 days, so it's drawing 200 examples at a time. We wouldn't be surprised if it doesn't find it immediately, but the moment it does, our tests go red, and they go red hard. You will spot that, and that shows up as a big red flag in your test runner. You need to go and fix something. So that's the examples database. That turns this from something, makes it something you really can use in your continuous integration suite. And the nice thing as well is, once you've done that, you can also, once you fix the bug, you can easily supply that example to hypothesis. You've not got to write another test, write that test separately. It's really easy to add that example, make sure it comes up every time after that. So you'll immediately spot when it regresses. So that's some of the stuff you get with hypothesis. You get a really rich API for generating your random data. You've got the ability to shrink random examples so that when something fails, you get a really easy to debug test case. And you've got the examples test database so that when it fails reliably and you're not stuck with flaky tests. So, how do we actually put this into practice? Because I often show this to people and they say, oh, that looks really interesting, it looks good on a slide, how do I actually go and use that in my code base? And obviously, it's, the hard part is always saying, what should be the properties? How do I know if the test passes? Because I don't know what code you're all writing, I can't tell you exactly, but you should look for things, what does it mean for your function application to behave correctly, but I'm going to show you, but since I can't tell you that precisely, I'm going to show you a few common test patterns, give you some ideas, some stuff you can go away and do immediately. So the first one, without knowing anything about any of your code, I assert that it should not crash. If I pass in random input to your function and it crashes, it's doing it wrong. So, we can make an assertion about that. Hypothesis, just generate random data with hypothesis. You should hopefully know what that data sort of inputs your function takes. So, pass them in using hypothesis and see, does your function crash? Or if it does does it crash with some very well-defined exceptions that you already know about? And if it doesn't, that's great, your code's probably okay. But there will probably be some edge cases that you forgot to think about. This is surprisingly effective on legacy code bases. I run this a lot on old coded work. I would say about at least 1 in every 2 to half the time, this flushes out some bugs, which is both nice and a damning indictment on the quality of some of our old code. So, pass with random inputs, and then start making really simple assertions about the output. Can your function ever return anything that's not none? If so, make an assertion. If it doesn't return none, does it return a consistent type? Make an assertion. If it returns a consistent type, can you put bounds on the value it will have? Make an assertion. You don't need to make complicated assertions here. Simple stuff is actually surprisingly effective at flushing out property application. Okay, thank you. Another one. This is one I call round trip. So if you have a function, and if that function has an inverse, you pass the data through both of them, you should get back to where you started. So this is good things like decoding, serialization, encoding, encryption logic, that sort of thing. So in this example here, I'm using the Python data tool library, which can parse a string, parse the data from a string. I'm using the datetime library, I'm generating random datetime, casting it to an ISO 8601 compliant string, and then I'm using datautil to unpack it again. Because that's a standard format, it should get this right every time. And then this happened. I was writing my slides on Tuesday, and then I find a bug in datautil library, which is really, really annoying when you're trying to write slides. That actually found 2 issues in datautil, and that is from 3 lines of code. 3 lines of tests to 2 bugs. That's a pretty good ratio. This again is a really powerful pattern. Okay, another one, test oracle. if you've got, obviously I said at the start, you're throwing in random inputs, you don't know what the outputs are, but if you've got an alternative implementation of your function, you know exactly what the output is. You should compare it to that. So this is a really good tool for if you're doing refactoring, or if you're optimizing code, or if you've just got a simple but slow implementation that you can't actually use in production, you can use this to make sure that your highly specialized version is working correctly. So as I said, I've been refactoring a lot of old code at work recently, and having this that is able to verify the old implementation matches the new implementation is really powerful and make sure that I'm doing an accurate refactoring. Final one, we've only got a few minutes left, I want to talk about briefly is stateful testing. Because all the examples we've looked at so far have been an instance of one function. I pass in a value, I get a value out, and that's fine. But most of the applications we write are not single functions, they are stateful, they have state. For example, a database might have reads, might have writes, consistency checks. You could have an individual unit test for each of those, but how do you know they all work together? How do you know there's not some sequence of reading and writes that triggers a bug? How do you test a stateful application? Now we could do what's often called an integration test. We've set up some sequence of those steps that we hard-code ourselves. We call that a test, we run it, we check that it works. But we're back to the same problem we started with, because those scenarios have to be hard-coded. We have to think of them. Well, what if we could apply this style of just doing random actions using hypothesis to our tests? It turns out hypothesis has hypothesis as well. This is one of the more advanced use hypotheses. This is really nice. What you do is you tell hypothesis, what sort of actions can you take? Then you tell hypothesis, after I've applied each action, how can I tell if the action is applied successfully? And then you tell hypothesis, well, go and try a whole sequence of random actions and see if you can break the application. So here's an example. I'm going to skim this. Okay, this is an example of testing a priority queue. We can push and pop items to the queue. I use the rule decorator to tell hypothesis, this is an action you can take. And after I pop an item to the queue, I check that it really was the item I expected to get back from the queue. Okay, so a fairly simple test, but it illustrates the principle. Hypothesis now goes and tries a whole bunch of pushes and pops with random data to see if it can break my queue implementation. And at some point, if I've written a bad information, it does, and it gives me a traceback that looks like this. This is an assertion that's telling me I popped an item from the queue. It wasn't the item I expected. That's bad. If you're running this code in production, that's all you get. You get a random traceback, and maybe if you're lucky, you have some logging from your database or stateful application to tell you what actions were taken before that. But that could be thousands of transactions. That could be, and you've got to work out what exactly caused that particular failure. So it turns out, a hypothesis course knows exactly what actions it took. And so it presents them to you as this really nice, broken down sequence. It gives you a runnable program that can you can go away and use to reproduce the exact failure, the exact state changes it took to lead up to that failure. This is incredibly powerful when you're trying to debug something, and of course, because we have shrinking, it's also going to try and give you a really minimal set of steps that reproduce this particular failure. This is definitely the more advanced end of what hypothesis can do. I've only used it a little bit myself, but it turns out you can do really powerful tests by not writing very much code at all. So, those are some test patterns. Fuzzing your code with random inputs, inverses and round trips. Use a test oracle or an alternative implementation to check your outputs are correct, and stateful testing takes hypothesis to another level entirely. So, briefly recap, property-based testing. Use random data to seed your test cases so that you get better coverage and better confidence that your code is behaving correctly. You can use hypothesis to do this in Python, although alternative property-based testing libraries are available in other languages. And we've seen some test patterns by actually putting this into practice, going ahead and using this in your code base immediately. If you want to learn more about this, slides are on my website already, and I'll post some notes later. The Hypothesis website and documentation has some really good material on both the library and this style of testing. And finally, David's running a workshop tomorrow. That's going to be a really good chance to get some practical hands-on experience with this library. And that's an introduction to property-based testing, an incredibly powerful way to find bugs in your code and make it more robust. Thank you all for coming.
So we've got no time for questions today, but another hand for Alex.